Recording is rolling. It is Tuesday, October 29th. Main focus today is going to be textbook puzzles. So I gave these to you guys a while back, but now we're going to start solving them. So chapter 8, well, it's a couple of parts from chapter 8, but different textbooks have these laid out a little bit differently. So rotational kinematic motion and centripetal force. We got a bunch of questions here. And on the backside are chapter 9 gravity questions, which I think I'm probably going to save for tomorrow. You guys are mainly in conceptual class, so see exactly how that takes us out. Before I do that with you guys, here, I got a Paul Hewitt for you. So we'll do a Paul Hewitt, and then we'll start solving those. Because we're going to go inside a spherical planet, like a spherical shell. A spherical shell. So this could be a hollow planet. What if you're trooping around the galaxy, you come across some planet, like, look, think it's something weird about this planet. You take your shovel, you dig down about a foot, and then suddenly it's a gaping hole opens up. You stick it in your head, you're like, wow, this whole planet is hollow. I'm walking around in an eggshell. Now you can walk around on the surface of that planet, but if you go inside, something weird happened.
In the center would have no gravity because it'd be pulled in all directions equally. Do we see that? But what I want to do is I want to convince you that it would cancel out no matter where you are. And so what we'll do is we'll take a point that's about here, where this distance here is twice this distance. Do you think it would still cancel out this side and this side? What we'll do is we'll consider a solid cone of material. We'll call this M1. We'll call that D1. We'll call this M2 and 2D. Well, just D and 2D. Let's look at our equation. Let's have the equation guide our thinking, gang. The force over here would be our mass, say the mass of the point, okay, times M1 divided by D squared. That's this force. The force that's pulling over here, you might think it's more because it's more mass. Or you might think it's weaker because it's further away. And guess what one does to the other? Okay. When you're out here, it'd be twice as much this way, but twice as much this way. So how big would M2 be compared to M1? Do you see it's 4? It's 4. So M2 would be 4 times M1. That'd be like 4 M1s times your mass, MP, divided by this distance here, 2D squared. But when I take the twice the distance and I square it, what do I get, gang? Isn't it like 4D squared? And what do the 4's do? And what's this? The same darn thing I got here. So you know what? The pull here, equal. I just took a place that was easy because I got twice the distance here as here. But you put any distance you want and that will happen. Anywhere inside there, there'll be no gravity. There'll be no field region. Inside a shell like that, there'd be gravity-free region. There'd be no gravitational field due to this mass. It would cancel out everywhere.
Yeah, that is pretty cool, isn't it? So I have a question for that. I picked a little bit different point. I did a 3R compared to R, but see, same thing. All right, so if it's 3 times far away, this is 3 times the diameter. But that means it's not only 3 times high, it's also 3 times far back into the page, which is 9 times the mass. Just remember about scaling. Now, I had the same thickness. Maybe it's a foot thick here, and it's a foot thick over here. Right? And so 9 times mass, pulling you to the left is pulling you to the right. But 3 times as far away, and that distance is getting squared. You guys remember inverse square law, right? So this 9 and this, well, 3 squared is also 9 down here. Those cancel. Yeah, so you can pick any point. So up and down it cancels, maybe kind of obviously, but right and left it also cancels too. I'm showing that here. Well, he would show that in a different spot. All right, so you guys ready for some puzzles? Puzzles. All right, let's flip over to your puzzles. I'm going to pick these up on Friday. I think this, whatever we do in class. All right, but let's see if we can knock out most of these in class anyway. First one, number 14. Calculate the tension in a horizontal string that whirls a 2-kilogram toy in a circle radius 2.5 meters when it moves at 3 meters per second on an icy surface. Ooh, so they're forcing it to be horizontal, which is kind of nice. We don't have to worry about falling down at some angle or anything like that. All right, so here's what we got. We got like an icy surface. All right, guys, icy surface, what's the coefficient of friction equal to? 0. So there's no friction. Okay. I got maybe a puck right here, right, on a string, and it's going around. Right. around in a circle, right? And the string has some tension in it, something like that. What's the tension in the string, right? So this mass right here, they gave as 2 kilograms. Plus we got this radius right here, R equals 2.5 meters. And, oh, and there's a tangential speed here. I call this V, right? It's always moving tangent to that circle, right? They gave that as 3 meters per second. All these values right here, I'll consider to be given values, right? Straight from the textbook, right? And here's your icy surface, got all that. So what's the tension in the string? Ooh, guys, is the tension acting as a what kind of force to keep it in a circular path? Centripetal force. Aha. Okay. So there's the first step right there. The tension force in the string is acting as a centripetal force. Let's get that. Right. Okay. Now, who knows an expression for a centripetal force? What's an expression for a centripetal force? Oh, yeah. What do you think? Just
Equals squared.
aha, mv squared over r, right there, like straight from your lab. That's the answer to your lab, isn't it? Right, this one right here. Right, let's do that. Let's do mv squared over r. Oh, we have m, we have v, we have r. Hey, I think I need to just plug that in. So I got 2 kilograms going at 3 meters per second. Square that. Radius of curvature, 2.5 meters. All together, 2 times 3 squared divided by 2.5. I'm getting a tension force in that string of this many. Is that many what? I need a unit. What's the unit? How do you measure force? Newtons. Yeah. Right. Also, here from these units, kilogram meter squared per second squared divided by meters. That's kilogram meter per second squared, which is what 1 Newton is. Yeah. About 7 Newtons. There's your string tension. If you cut the string open and you put in here one of your spring scales, what is that spring scale going to read? 7.2 Newtons. Okay, number 48. An ice puck with some mass m revolves on an icy surface, circle speed v, end of a string, length L. The string tension is T. Hey, it looks like what we just did, except now it's in terms of variables. Just like if you replace the numbers with variables, it's the same thing for number 48. Question A, write an equation for a centripetal force and substitute in the values for tension and length. Then what bit of, with a bit of algebra, rearrange the equation to solve for mass. That's interesting. All right, so number 48, which looks a lot like number 40, just in terms of variables now. So you guys think the tension force would have to be mv squared over r? Like that would be true, right? Right. Now they're saying, okay, they're calling the tension force just capital T, right? Sometimes I try to avoid that because capital T can be used for time period, but let's just go ahead and just stick to what the book is. So in place of tension force, I'll just call it T for tension. T is tension because that's what the book has. Right? They want you to solve for the mass, and did they give you? Yeah, okay. They went ahead and said speed v. That's being squared here, right? And instead of r, guys, what property of the string represents the radius r? How about the length of the string? Right, the length of the string L. Right there, right there. Everybody does have these puzzles, right? I accidentally printed way too many of these, so totally walk around, make sure everybody's got these. You guys got some puzzles. Right. Guys got these puzzles. Okay. All right. You guys have these. All right, so now we're supposed to, with some algebra, solve for mass, right? Like, remember I was saying before, if you cut the string open, you threw a spring scale right there, right? Suppose you read it straight off the spring scale, say, okay, see what value it is. You have a speed gate here and puck goes through a speed gate, so you know how fast it's going. And you measure with the meter stick the length of the string. You wonder, hey, I wonder what mass puck that's on the end to make all these other variables be exactly whatever measured values they are. Okay? Can you guys do the algebra? Go ahead. Do the algebra. What have you guys can solve in terms of variables? Okay. Give you guys a head start. You guys can do that. Oh, get some more scrap paper on my stools out here. Okay. Give you guys a shot to solve for top of that math right there. Okay, you guys got some paper. Okay. I'm gonna pick these up, puzzle up for you guys. What I'm really looking for is your thought process, your work. Okay, you guys can. Everybody's got some paper, like. Yeah. Do that. Okay. Oh yeah, just a minute here. I'll get it to you. Okay. All right. So guys, can you just cross multiply the L and do tension times L equals mv squared, and then just divide both sides by v squared. So m equals t times L over v squared. I think that's it right there, right? So if you read the tension straight off this, because you have a spring scale in there, so, oh, the tension is like 7.2 newtons or whatever, okay? And the string is so many meters long. And I know how fast it's going because it got the speed gate and it tells me exactly how fast the puck's going through the speed gate, right? Then I could calculate how massive that puck is. That's what that could be. Right. Right. And here, there's another part to this. It says, show that this is part B. Show that the mass is 5 kilograms when the length is 2 meters, the tension is 10 newtons, and the tangential speed is 2 meters per second. Oh, whoops. Okay. I think this bit down here is a misprint. Okay. I think oops. Okay, so ignore everything right beneath that. Okay. But let's try this out. All right. See, does this work? So I'm saying mass is equal to tension times length divided by v squared. Okay. Let's do it for, they said the tension is 10 newtons. I'll plug in 10 newtons for the tension. They said the length is 2 meters. Plug in 2 meters for the length. And they said the speed is 2 meters per second. Okay. We got to square that down here. Okay. Let's see, what does this come out to? Guys, what's 2 squared? 4. What's in the numerator? What's 10 times 2? So I got a 20 there, I got a 4 there. Now this is newtons and meters on top. This is meters squared per second squared down here. Okay. Now a bunch of this stuff cancels. Guys, is 1 Newton 1 kilogram meter per second squared? So it's like, you got kilogram, meter, and then times this meters, meter squared per second squared. Down here I have a 4 and a meter squared per second squared. All those meters are set in seconds. Go away. I'm left with kilograms. What's 20 divided by 4? 5. Right. There's 5 kilograms. Oh, and that's what they wanted you to confirm. They said confirm the mass is 5 kilograms when given all these other numbers. And that's exactly the answer. Yeah, so check it out. Right. This is a nice thing about solving in terms of variables, is that you have like a master equation that can solve any scenario. You just plug in numbers so you could, right? Like you have like a string of questions and you just solve the same thing over and over and over. Right? Plug in anything. All right, so you guys get on 40 and 48. Okay. All right, next one. Oh, here, let's amend this a little bit. You guys see this text right here? Go ahead and scratch this out. I think that's a misprint. I had a fuller question there. I think it got covered up, so we'll just ignore that. All right.
Which number?
Well, it's not numbered, but you guys see underneath 48? You guys, there's a 48A, there's a 48B, and underneath that, there's like 3 lines of text that was like hanging over from some question. But the full question is not there. If you read it, it doesn't make any sense. So we're just gonna skip it. Okay. Also, I have another misprint in the title. I may have scratched this out with you guys. I don't know why I typed centrifugal, probably because it was late at night, but I meant centripetal. So oops. All right. 56. While riding on a carnival Ferris wheel, Sam Nasty horses around and climbs out of his chair and along the spokes, so he is halfway to the axis. how does his rotational speed compare with that of his friends who are in the chair? How does his tangential speed compare? Let's get a picture going. All right, so 56. All right, got a big old Ferris wheel. All right, we're gonna throw some spokes on this Ferris wheel. Good. All right. And say most people are like in these little booths. I'll draw some booths around, right? Going around the edge. Right. Then we got Sam Nasty, and he's climbing. He's like right here, like monkeying around right there. So you see him right here. Right. So all these booths were at maybe some radius r, but he's down here at radius r/2, like half the radius. Right. So how does his angular speed compare and how does his tangential speed compare? Here, I'll treat those two separate questions. So question A is, let's go angular speed. Angular speed, that's omega, right? Is that, because if this whole Ferris wheel is turning all together, it's like one solid disk. Is that the same angular speed everywhere? The same angular speed? Yeah, it's the same everywhere on the Ferris wheel. Okay. Now, what about tangential speed? Like, guys, what if he climbed all the way to the very center? What was his tangential speed be right at the very center? 0. Yeah, 0. He wouldn't be moving anywhere. I mean, maybe he's getting dizzy. That's about it. But down on the edge, I think you're moving some tangential speed. Tangential speed, I'll call it like v, right? Do you guys remember this right here? Right, turntable. You guys did this turntable lab. You guys remember that? You set some coin some distance from the center, right? And if you know how fast it's rotating in radians per second, multiply by your distance from the center, you get your tangential velocity at speed. Right? Well, guys, if he's at r/2 because he's halfway out, right? Like here's all his friends out here. Here's Sam Nasty. He's halfway out, and everybody has the same tangential. Sorry, the same angular velocity. I meant to say the same angular velocity, but you're halfway out to the edge. Do you think you have half the tangential speed? Yeah. So I'll back it up with this equation. I'll say v equals omega times r, right? And if this omega is the same everywhere, okay, and this r is like, well, r/2, right? I think Sam has half the tangential velocity of his friends on the edge. Okay. Half the speed. You guys good?
You just read the.
Sam has half the tangential. Oh, angular speed is the same everywhere on the Ferris wheel. So the angular speed is the same everywhere. They all get the same turns per time, right? But their linear speeds are different. If you're right in the center, you have 0 linear speed. The further out you go, the faster you're going. In fact, how fast you're going in a linear sense is just proportional to your location from the center. That's all this says right here.
He climbs onto the bottom.
Yeah. So, guys, you've been on a Ferris wheel? You're like sitting in these booths. Here's all his friends in the booths. Right, they're where they're supposed to be. Okay. Sam Nasty is going to climb outside the booth. He's going to climb up this Ferris wheel, and now he's like monkeying right here.
I hope the right is turned on.
Oh no, it's spinning. But that's good. He's cartoon, so he's probably gonna be all right. Yeah. 57. Dan and Sue.
Why did you do this disclaimer of don't do this at home?
Because I'm assuming you guys probably don't have a Ferris wheel at home. Right? It's a deep assumption, I guess. Dan and Sue cycle at the same speed. Now, guys, when it says same speed, they probably mean the same linear speed, right? Right? The tires on Dan's bike are larger than those on Sue's bike. Which wheels have a greater rotational speed? Ooh, let's draw this out. 57. So let's do Dan and Sue. Right. So they say Dan's tires. Yeah, thank you. Are larger diameter. Right. Let's get a big old bike going here. So here's Dan and his bike. It's got really long Dan arms. Right. And here's Sue's bicycle. Got two arms. Okay. And they're both traveling at, well, the same linear speed. They're going side by side. So whatever V that is, that's the same V. Same linear speed. Right? Right. Now,
You're a paper.
remember, all right. Yeah, just go and sit on a desk and, yeah. All right. Thanks. All right. So, hey, remember this one right here? This omega is how fast is the wheel spinning about its central axis. Right? This V could be how fast is any point on the tire moving. Okay, maybe like okay, so right, something like that. Right. And so which is faster? And we got two different radial sizes. So let's do in general V equals omega times R. Okay. Okay. Now here's here I'll set up two of those equations. V equals omega times R. Right? Because it's the same speed for both, so these V's are equal to each other. Right. But they've got different angular speeds and different radial sizes. So here's D for Dan, and here's S for Sue. And here's D for Dan, and here's S for Sue. Okay. Let's do a numerical example. Like, what if they were going 24 meters per second? 24 meters per second. So they're traveling side by side. Got the same linear speed. Right. I'm just gonna make up some numbers. Suppose Dan's tires were like 4 meters diameter. And what if Sue's tires were like 3 meters diameter? Just make up something crazy. Right? If you're not sure how something plays out, just throw in some numbers and see what happens. Maybe it'll tell you some kind of insight. Okay? So who now can tell me how fast is Dan's tires rotating? Could it be 6 radians per second? And then how about Sue's tires? How fast are they rotating? 8 radians per second. 6 times 4 is 24. 8 times 3 is also 24. You guys see that? So they travel the same speed. They got different sized tires, therefore they have different angular velocities. Right. So now, how exactly was the question worded? Which wheels have a greater rotational speed? Right. So if I do here, let's do an inequality. So omega for Sue compared to omega for Dan. You guys got that? Okay. All right. I need an inequality sign. Guys, which way does the inequality go? Whose tires are rotating faster? Sue's. Yeah. Like that. You've got itty bitty wheels. You have to spin real fast. If you got giant wheels, they just go real, not spin very fast at all. You can put them right next to each other. So this guy's going, this guy's going, and it could be traveling side by side. Right? All right. Let's all right. Here, we're gonna skip a little bit. Let's just do 59 verbally in class. It says the wheels of a railroad trains are tapered, which is important for curves. How does the amount of taper relate to how sharp the curves can be? All right, so we could draw a picture for this. Let's so we're skipping 58. Let's just go to 59. Okay, and see wheels on a train. As if you look at a train wheel on a track, here could be your track. Here's railroad track, like a cross section. You guys see yeah, let's see you're looking at the track. It's like going into the horizon, right? Got plank, plank, plank. Okay. You guys see this railroad tracks Okay, see this? Right. Here could be the wheel of the track, or sorry, the wheel of the train. Maybe it's shaped kind of like this, for example. Like tapered. I see it's like tapered like that. Right? Because this kind of locks in place, doesn't it? Kind of locks in place.
Yes.
Right. Now, what if this train was like going around a curve? Going on a curve. Right? Do you think this might want to be starting to slip off? Right? Like
58?
we're skipping 58. Okay. So skip 58. It just well, here, we'll come back to 58, but we're just doing okay.
Are we doing?
Okay, yeah, go ahead and yeah, draw. Well, we'll just do this verbally. We're just doing it verbally. Right. So yeah, you don't have to do this. Right. But I just want you guys to think about this though. So, like, what if there was no lip at all? And this train would probably fall off the tracks easily, especially if it's going around a curve. It'll slip off real easy. Okay. But maybe the more lip it has, right, the faster it could go around a curve, and the tighter curve could go around. Okay, just think about that. Okay. Oh, we're gonna skip that. Skip. Let's do number 80. Number 80. A racing car on a flat circular track needs friction between the tires and the track to maintain circular motion. How much more friction is required for twice the speed? Ooh, this is a good question.
Did you skip 59?
Yeah, okay, guys, we're gonna skip 58 and skip 59. We're skipping those. Skip. Let's go straight to number 80. Number 80. Right. So a car on a circular racetrack. Let's get a car, wheels, license plate, tail lights, rear view windshield, right? And it's on a circular track. So circular path, it's going around. Okay. You guys see it's like going into the page, it's making a turn. Let's do a free body diagram. We'll do the full version for this one. Free body diagrams. Guys, what force is pulling straight down on the car? Weight, mg. What force is holding the car up? The normal force, which is equivalent to mg, by the way. It's a flat track. Okay. Now, guys, as the car is moving forward, it's also turning to the left. What force is allowing the car to make a turn to the left? Friction. It is friction. Friction force. Right. There's your free body diagram. FBD. FBD. Free body diagram for the car. All the forces. Right for that. Okay. Now, this friction force is acting as the centripetal force. Friction force is equal to, hey, do you guys know an expression for centripetal force?
M squared radius.
Yeah, mv squared over r. mv squared over r. Hey, that was the answer to your guys' last lab. Right, you guys know that? Lab. Right. So here, if you drew like a circle here, I bet the circle has some radial size. I'll call that r. Right? Whatever radius of curvature that this is on going around, that's what that r is right there. Okay. Right, guys good? Right. Now, they said, what if the car has double the speed? How many times the friction do you need? And I think you can see it right here. I bet some of you guys already know the answer. Guys, if you have twice the V, how many times the friction is that going to be? 4 times. 4 times. Because guys, if you throw in a factor of 2 on this V, it's also going to get squared. 2 squared is 4 times the friction. The answer is 4 times. Right. So here, I'll jot that down here. Twice the speed requires 4 times the friction. That's the answer. 4 times the friction. All right. Now, here, let me try to back that up with some numbers. Suppose, here, crazy example. Suppose the mass was equal to 1 kilogram. The radius of curvature was 1 meter. Maybe we got a little tiny toy car. Run around. Let's say the initial was like 1 meter per second. You guys got that? All right. 1 kilogram, 1 meter radius, 1 meter per second. Right. What would the friction force be? How much would that be? 1 kg times 1 meter per second. Square that. Divide by 1 meter radius. Isn't that like 1 Newton? 1 Newton of force. Okay, now let's double the speed. Okay, so the new friction force equals, okay, so the same mass car, 1 kilogram, times, now we're going to 2 meters per second. We're going to square that and divide by the same 1 meter radius, right? Hey, how many newtons of friction is that? 4. Is that right there? Right. And if you compare these, that's a 4-to-1 ratio, right? Now, I know I did real simple numbers, 1 kilogram, 1 meter, 1 meter per second. Guys, I could have made up any numbers. Or I could just do it in terms of variables. And when you double the speed, you're always going to get 4 times the force. Right? This is one set of numbers, but you can put in any numbers and you'll always get a 4-to-1 ratio. Okay, you guys get that? 4 times the force. All right, you guys good with 4 times the force? 87. The occupant inside the rotating space habitat of the future feels she's being pulled in by an artificial gravity against the outer wall of the habitat, which becomes the floor. Ooh, yeah. Explain what's going on in terms of Newton's laws and centrifugal. Here, we'll just draw a picture for this. Let's just draw a picture and then we'll move on. So 87. Can you guys call this O'Neill cylinder? Right. Draw a big old picture. And then, guys, if you're walking around this O'Neill cylinder, got some radius R. I guess it's rotating around. I'll call this omega, maybe something like that. Guys, where are you walking? Can you draw a stick figure to show where you're walking? You're walking around on the floor. Which floor are you walking on? Can you guys draw a stick figure? I want to see where you guys put a stick figure in your picture. I'm going to walk around. I'm going to walk around the classroom and check out you guys' O'Neill cylinder. See, where did you draw the stick figure walking around?
Option required.
Inside around.
Aha, all right, winner. I got to draw the stick figure.
Actually,
All right, you guys getting this? Figure out where to draw this guy. All right, yeah, winner. All right. Yeah. Oh, sorry. All right. Yeah. You guys drew him right here. He's walking around on the inside. Right? You guys got that? And the floor, like he feels the force on the floor. Like right now, you can walk around the floor. Be like, okay, I feel like I'm being pulled down by gravity, but the floor is holding me up. So I got that. This guy right here. What force or forces are what's one force on this guy? What's one force? Wait, does he have a true gravitational weight? No. Guys, there's no real gravity. What force is acting on him then? Normal force, exactly. That's this right here. So I'm gonna draw a force vector. I'm gonna label this the normal force. Is that it? Is that the only force? Yeah, that's it. I could maybe draw a velocity. That's not a force though. Got this tangential velocity. Guys, if the floor fell away, suppose this thing's spinning, it's all fine and good, it's up in space. And then one day the floor just dissolves, just disintegrates. Which way is this guy gonna fly off? I'll give you guys a couple options. Does he fly straight away from the center? Or does he fly off tangent to his path? How many of you guys say the second thing I said? How many of you guys say he's gonna fly off tangent to his path? It's gonna fly off that way right there. Who thinks that? Yeah, he would do that if the floor just disappeared. Or if it was a ball on a string, you cut the string. Same story. All right, so you guys good with that one? All right, so be enough right there. 88. Sketch shows a coin at the edge of a turntable. The weight of the coin is W, so W for weight, I guess we're doing. The other forces on the coin, normal force and the friction force. Draw vectors for both those. Let's do that. Let's draw a free body diagram on 88. Turntable. Here's your turntable. Here's your coin. Here's the center of the turntable. Here's the axis of rotation. And this whole thing is rotating omega, some number of radians per second. There's the setup. Okay, let's get some forces. So do is center of mass dot on this coin. We're focused on the coin. Okay. Now they gave you one force. They said, oh, this coin does have a weight. So let's go ahead and label that W for weight. Okay. Guess what's another force acting on this coin? Normal force. Ah. You guys draw. Oh, how long should you draw that normal force? Yeah, same as the weight. Has to cancel out the weight. Okay. Now guys, if this coin is staying on a circular path, I bet there has to be another force on it. What forces keep allowing it to move in that circular path? Friction. And which way is the friction point? Towards the center of the circle. Guys, draw that vector and call it FR. Friction force. Friction force. All right, guys got all those. All right. Guys good? All right, what got next? 101. An automobile speedometer is configured to read the speed proportional to the rotational speed of the wheels. True. Guys, like how does your car know like how fast it's going? Well, it doesn't really know how fast your car is going relative to the outside world. What it does know is how fast the wheels are rotating. And if it knows the radial size of the wheels, it can calculate how fast the car is going. So, guys, when you look at the speedometer of a car, the car says they're going 54 miles per hour, something like that. That's really a calculation. It comes from knowing how fast the wheels are turning. That's this omega times the radius of the wheel. So, oh, the car must be going 54 miles per hour, something like that. Okay. All right. So, where are we going with this? If oversized wheels of this red car were installed without making speedometer corrections, then is the speedometer reading going to be high, low, or no change? Well, it's not going to be no change. There will be a difference. Right? Is the speedometer going to say the car's going too fast or too slow? So let's compare regular wheels to large wheels. So I got a car with regular wheels on it. I got a car with big wheels on it. Something like that. Something like that. And I have an equation. It goes V equals omega times R. Right. So think about guys, if this wheel makes one complete rotation. There's one complete rotation. Here, guys, who can tell me how far is the car moved forward as a function of the radius of the wheel? Guys, what? That's a good challenge question right there. Guys, the wheel makes one complete rotation. How far forward did the car move? Two pi r, right? Would it be one circumference of the wheel? Because every bit of that wheel, right? Right. So if we're going from little wheels to big wheels, right? Little wheels to big wheels. And let's say this wheel makes one rotation. The car moves this far forward. Goes that far. This wheel makes one complete rotation. The car moves probably about that far. You guys see this car went further than this car? Right? With the same rotation. Now, if the speedometer just knows one rotation, one revolution, you could put like a 2 pi right here. So, okay, I'm going to plug in 2 pi for this one. Maybe I should do radians per second. So it's like 2 pi radians per second, right? Something like that. Right? And knows the radius of the wheel. Well, if the radius is too big, if this is too big, then the calculated tangential speed is going to be 2 what? Because if the radius of the wheel was like 5 times as big, then when the speed calculated be also 5 times too big. That's it, right? So, guys, suppose you were in this big car or this car with the big wheels. You're driving down the highway, and it says you're going 54 miles per hour. Are you really going 54 miles an hour?
No.
No. Are you going more than that or less than that?
More. Less.
I think you're going less than that. right? Maybe you're only going like 20 miles an hour, right? So you're going real slow. You're going real slow because you're watching all the other cars whiz by you, but your speedometer doesn't know that because your speedometer is saying, "Wow, those wheels are like turning like crazy." Or sorry, sorry, other way around, right? Those wheels are hardly turning at all because they hardly have to turn at all to propel the car forward. Right? So the speedometer, see, wait a minute, did I get that? Yeah, so for every one rotation. Dude, did I do that right? Yeah, okay. It's gonna tell you you're moving faster than you're actually moving. All right, that's it. The speedometer reading is gonna be too big. Yeah. All right. 102. Here, this will be the last one for today. 102. A large wheel is coupled to a chain with a small wheel, half the diameter, just like that picture. How does the rotational speed of the small wheel compare with that of the large wheel? Right, and then what about the tangential speed? So last one today, 102. Okay, so got a small wheel, a large wheel. This has maybe radius r, and this could be radius 2r, and they got this chain going around them. Right, so they're all tethered together. Right? So omega small, omega large, right? And then v small and v large. Right? Guys, do you guys think that this belt has a constant tangential speed everywhere? Right? Therefore, any point on the edge of these two wheels also has the same tangential speed. I'm going to say these two are exactly equal to each other. You guys get that? Right? So this belt's moving around with a constant speed. Right? Now, if that's true, then suppose it makes the large wheel turn around completely once. You guys got that? Here, I'm about to make a connection here. V equals omega r, or if you like, omega equals v over r. Right? So they got the same speed. This large one has a large radius. So it's not spinning very fast at all. Suppose it turns around once. How many revolutions has the little guy made? 2. It only has half the radius, so it'll be twice the number of turns. Right? Yeah. So double the radius would be half the rotation. Half the radius would be double the rotation. So I'm gonna say this right here. Okay? Or actually, if you want to make an exact equation, it goes like this: omega small equals 2 times omega large. Rotation to rotation. Yeah, I think that looks about right. All right, that'll be our pause point today.